Hello everybody, thank you for coming today. My name's Emma Dutton and I'm the training manager here at Solax Power. I'm a fully qualified electrician with over 20 years experience, and today I'm going to be introducing you to the new X3 IES.
Today's webinar will mainly introduce the appearance, installation advantages and highlights of IES. If you have any questions during the webinar, please do not hesitate to contact us with the chat button in webinar. If you cannot hear the sound while listening, please change the audio device to the default in the device settings of the webinar or log in again. With the development of energy storage systems and advancements in artificial intelligence, energy storage systems have gradually evolved from single products into versatile solutions that can adapt to different application scenarios. Our original intention of developing IES is to provide installers and end users with convenient installation and intelligent usage scenarios to meet the different needs of customers. The capacity of the 3 IES ranges from 5 kilowatts to 15 kilowatts, and the battery capacity of 10 to 30 kilowatts hour can be connected through the BMS. The usage scenarios can be used in apartments, semi-detached, detached, farm and commercial scenarios. Now let's take a look at the appearance and size of IES. That currently only supports battery HS50E. Each battery has a capacity of 5.1 kilowatt hours. Three-phase IES support 2 to 6 batteries connected to the BMS. The battery installation method is stack installation, and there is a base at the bottom to improve stability and prevent groundwater accumulation. The connection and communication of the battery are integrated inside through the bayonet, which avoids wiring problems and communication problems that may occur during installation and use. IES can connect up to 10 sets of equipment through parallel box to provide an energy storage solution of 300 kilowatt hours. Even if you install a 180 kilowatt hours IES in the early stage, it is very easy to expand the capacity to 300 kilowatt hours after using it for a period of time. Most batteries currently on the market are IP55 and hybrid is IP65. Our IES is one of the few solutions that can achieve IP66. It is a more reliable choice whether in indoor and outdoor scenarios. Now, let's explore the functions and parameters of IES. After understanding the parameters, I will show you how to install it. Last, we will introduce the solutions IES can provide and its working modes in different scenarios. IES is a set of solutions full of advantages and competitiveness. High performance, AI-based, bill-saving, reliable quality and easy installation are the main highlights of this solution. Easy installation and match the wireless meter. It usually only takes half an hour to complete the entire IES installation. I will show you the installation steps and process.
We are going to install the X3 IES system with 3 5 kilowatt batteries. Ensure that the base is fully secured to the floor. So I'm going to install one 5 kilowatt battery onto the base. Each side has a screw to keep it secure. When each of the batteries is installed, we're going to put 2 screws either side to secure it in place. We have installed 3 5 kilowatt batteries. This is the BMU, Battery Management Unit. Again, ensure that it is screwed in place. Next, we're going to install the 15 kilowatt hybrid inverter. For this, I'll need another pair of hands. Okay. So here we have the X3 IES system, 15 kilowatt hybrid inverter with 3 5 kilowatt batteries. On the left hand side of the BMU, we have the battery isolator and the power button. On the right hand side of the inverter, we have the communication port. We have the CT meter port, RJ45 connector. 2 MPPTs with 3 string inputs. Cable connections for the grid input and your EPS power output. Isolator, on-off switch, and your USB connection for your 4G dongle, LAN dongle or Wi-Fi dongle.
As demonstrated in the video, the installation of IES can be completed by laying bricks. Compared with the traditional installation method, it is more concise and elegant, and at the same time, it avoids the trouble of repeated visits to the site caused by wiring errors. Compatible wireless meter is also another key feature of IES. In the traditional electricity meter scenario, there are often many problems with the configuration or wiring of the electricity meter. Building or outdoor wiring is difficult and unsightly. The wired communication distance of the electricity meter required within 200 meters, while the wireless module only needs to be connected to the inverter side. AP module, connected to an STA module on the side of the meter, can realize communication between the inverter and the meter. The communication distance of 300 meters in open space is larger than traditional wired communication. It can be separated by up to 4 floors, saving installation and wiring time. The wireless module is installed on a standard rail. The meter side can be directly attached to the side of the meter. The cross sections are similar in size and can fit together. It supports 85-277V voltage input, IP20, and comes with a magnetic base antenna. The antenna is installed on the outside of the distribution box. The antenna is wired 1 meter. Wireless modules need to be used together. Currently, a set has an access point and a station module. It also supports 1 AP with multiple stations modules to achieve dual meter solutions. Inverter oversizing means installing an inverter with higher capacity than your solar panels. Benefits include improved energy harvest, increased system efficiency, cost effectiveness, and future expansion capabilities. Solar panels often produce more power than the inverter's capacity, and oversizing helps utilize this excess energy. It also enhances system efficiency and allows for future scalability. Oversizing can be cost-effective as it generates more energy without extra panels. Consult a professional installer for optimal inverter sizing. Most of inverter in the market do 150% oversizing, but IES can do 200%, 100% AC output use, 100% store in battery, 20 A input current per MPPT that's compatible with all PV panels, including high-powered ones. The 10 mA automatic switch over in inverters sets a new standard for uninterrupted power supply. With its remarkable response time of just 10 milliseconds, it ensures a seamless transition from the main power source to a backup power source. This rapid and efficient switchover minimizes any disruption, allowing critical appliances and devices to continue operating without interruption. The 10m's automatic switchover showcases the enhanced reliability and performance of modern inverters, providing businesses and households with the confidence that their operations will remain uninterrupted even in the event of a power outage. Its precision and speed make it a valuable feature in ensuring uninterrupted productivity and convenience. IES supports power supply to half-wave loads, ensuring basic life needs as much as possible in case of power outage. With unbalanced output function, the inverter output power on each phase depends on the load consumption of each individual phase. Output power is then shared between phases before metering or exporting to the grid. IES also support 100% unbalanced output. For example, inverter max output power is 33%. So 100% unbalanced output means the potential unbalance range is 0, Bobra 33%. For reliability and safety, We support AFCI and rapid shutdown as optional. Type 2 SPD on AC and DC side and using cobalt-free LiFePure4 battery. In IES, we have also added another work mode, time of use, whose working logic is based on hourly time units of a week, and users can independently select the working mode for each time period. The optional modes include the modes mentioned earlier. We will show you more details about settings in future webinar. During the installation, the capacity of PV is often greater than the capacity of the inverter. In the case of large overconfiguration, when the sunlight is strong, the PV power generation is greater than the inverter power, and the excess will be discarded. At the same time, some countries, such as Germany, the United Kingdom, Belgium, Australia, etc., have grid-connected power limit requirements for photovoltaic systems. Electricity exceeding the grid-connected limit will be discarded. Smart Schedule can automatically adjust the working mode according to power generation, electricity consumption, and electricity price fluctuations, perform peak shaving and valley filling, or control battery charging and discharging time to maximize economic benefits. Customers can customize the charging and discharging of the inverter based on conditions such as time, weather, meter, data, electricity price. Customers can set their own settings according to usage scenarios. For example, you can set it to turn on the EV charger when the time is 3 p.m. every day. IES also support integrate with VPP platforms and other platforms through API or OpenADR. Even you already have other brands' PV inverters. That system still can work with IES to make system works when off-grid. What only need is the whole set of IES and extra meter or CT. Generally speaking, these relevant numbers can summarize the advantages and highlights of IES. After the training, we will send the training materials to you via email. Now let's see the different scenarios of IES. This system provides backup power to specific loads or appliances during a power outage. This means that even if the grid goes off, certain essential appliances or loads can still be powered by the energy stored in the system. To ensure that critical loads such as refrigeration, lighting can continue to operate during a power outage. Usually, we call the load connected to the EPS port of the inverter as the critical load and the rest as regular loads. We can see in the figure that the critical load and regular load connected to the inverter are independent circuits, and the built-in switch can ensure that the off-grid switching is completed within 10 minutes. Install a Solax meter or CT at the mains port to achieve zero control input to the power grid through the built-in output control function. It is also necessary to install MCB, RCD and other protection equipment externally to protect the electrical appliances and inverter on the circuit. This system eliminates the need to separate loads into critical and conventional loads and is able to provide backup power to the entire home in the event of a power outage. This means that electrical loads, including appliances, lights and other equipment, can continue to operate during a power outage. As shown in the figure, the wiring of the whole house load is different from that of the separate house load on the previous page. An external ATS switch is usually required. Taking Matebox G2 as an example, connect both the grid and EPS ports on the inverter side to the Matebox. Then both the critical load and the regular load are connected to the load port of the Metabox. When there is mains power, the ATS switch automatically closes to the grid side to supply power to the load terminal. After the power is cut off, only the EPS port outputs and the ATS switch automatically closes to the other side, which is also connected to the load terminal. Port to supply power to all loads. The connection of the communication line is as shown in the figure. We connect the communication line of the sampling device inside the box to the meter CT port of the inverter. Load communications such as EV charger and heat pumps are directly connected to it by the inverter. This system can be used when there is no mains power supply at all, such as scientific research construction or scenic spots facilities in remote mountainous areas or islands. The generator will act as mains power to supply power to our entire system load and charge the battery. There is an important requirement in the selection of generators. That is, the total power generated should be greater than the sum of the total power of all loads on the line. As shown in the figure, the grid port of the inverter is directly connected to the generator, and an indispensable CT is added to achieve precise zero control to prevent the battery current of the energy storage machine from flowing back to the generator and damaging the equipment. All loads are connected to the EPS port. This is to ensure that when the generator is not working, that is, in the off-grid state, the inverter switches to only the EPS port output, and our loads can also supply power normally. This system requires a generator with dry contact function. As shown in the figure, the generator has a communication line directly connected to the inverter. In the dry contact mode of the generator, when the power is sufficient, the battery will be used first. When the battery drops to min. When the SOC value is reached, the inverter tells the generator to start through this communication line, charge the battery at full power, and supply power to the load. Until the battery is charged to SOC, the generator stops working and switches to the battery to power the load. The difference between this system and a pure off-grid solution is that it has a mains power inlet and the generator is used as backup mains power. This solution is often used in remote areas with unstable mains power and frequent power outages to maintain the operational stability of access loads. And the output power must be greater than the total power of the load. As shown in the picture, there is an ATS switch included with the generator. This has also appeared once in the whole house load solution. Its function is to pull in the generator side after the mains are disconnected, and the generated electricity, the machine acts as backup mains power to ensure the normal operation of the entire system. The selection of sampling equipment is very critical. It requires a CT and an electric meter. It is worth noting that an electric meter must be selected on the side of the mains to ATS switch. The function of this electric meter is not to collect the current and voltage information of this part. It only needs to judge the current voltage. Check whether the electricity is disconnected. When the mains power is disconnected, the electric meter cannot work and the inverter side cannot receive the communication signal from the electric meter. From this, it is judged that the mains power is disconnected and the generator enters the dry contact working mode. The CT does not have the function of judging whether the power is cut off. Look at the side of the inverter to the ATS switch. We recommend using CT because CT responds quickly and can prevent electricity from the energy storage battery from flowing back into the generator and causing damage. The layout of the entire system is very simple. You only need to add the ATS switch that comes with the generator to the original split house load energy storage system. There are no complicated circuit modifications or complicated function settings. This page is mainly talk about parallel solutions. In order to meet greater power consumption requirements, such as adding charging piles, heat pumps and other loads, the system adds a parallel solution based on the above-mentioned generator system. As shown in the picture on the left, for 3 or less IES, you only need to merge the lines of the grid port and EPS port to connect to the regular load and emergency load respectively. The wiring and working logic of the generator test are the same as those above. The plans are consistent. For 4 or more IES, we need to use an auxiliary tool, the EPS parallel box. Because after multiple devices are paralleled, in order to ensure the consistency of the parallel and off-grid switching of multiple devices, we change the internal switch into an external switch. The working principle is basically the same as the ATS switch mentioned in the whole house load. That is, when multiple devices are switched in parallel, after paralleling, the whole house load is also realised in disguise. Sampling equipment is still essential, just be on the side closest to the mains. So, microgrid solution is also common in the market. There are a large number of conventional grid-tied inverters on the market. Due to the islanding effect, the grid-connected inverter cannot work when off-grid. This feature causes users to lose the photovoltaic energy of the grid-connected inverter when going off-grid. The microgrid solution allows our energy storage inverter to simulate the mains power and activate the grid-connected inverter in an off-grid state to utilise its photovoltaic energy. As shown in the figure, the grid port of the IES is directly connected to the mains power. After the EPS port is connected to the emergency load, it is connected to our grid-connected machine through a line. Regardless of whether the mains power is disconnected, the output of the EPS port will be supplied to the grid-connected machine. Provide mains power. If the PV is sufficient at this time, the energy on the grid-connected machine side can supply power to the load and charge the battery. It is worth noting the choice of two communication devices here. Considering that in a three-phase system, CT communication will cause the energy storage machine to be unable to distinguish the source of information due to the same signal channel, so here we use two different sampling devices, CT and electricity meter, so that distinguish. And because the CT information received by IES comes from the mains port by default, the positions of the meter and CT cannot be interchanged. After wiring as shown in the figure and enabling the microgrid function, it can be used normally. Here is an additional scenario. In the off-grid state, if the battery is fully charged and the load stops working, and the PV is sufficient at this time, since the IES cannot directly control the output of the grid-connected machine, it will increase the output frequency of the EPS port and activate the grid connection. The machine's over-frequency load reduction protection function, thereby limiting the PV output on this side of the grid-connected machine.
And grid forming zero injection. Data hub plus mega plus hybrid. This solution is widely used in high power scenarios, such as industrial and commercial settings. Integrating an energy storage system and parallel system into the data hub solution aims to meet the requirement of ensuring partial critical load usage during hours when there is no PV. As shown in this solution, the wiring of the energy storage and paralleled systems align closely with the requirements mentioned earlier for the parallel solution. Connecting 3 units or fewer is a direct parallel connection, while from 4 to 10 units, the EPS port needs to be unified into an EPS parallel box for centralised control. There are 2 electricity meters required in this scenario. The electricity meter on the grid-tied inverters detects the current passing through the loads, and the meter's communication feeds into the data hub, which then manages this part for the zero control command. The meter closest to the mains electricity supply provides information to the energy storage inverter, responsible for controlling the entire system's zero control. Work mode. Several operational modes are suitable for almost all demand scenarios. The self-use mode is commonly used in areas where electricity prices fluctuate significantly. In this mode, the discharge priority for PV is to supply the load first, then charge the battery, and finally send any excess back to the grid. The feed-in mode is prevalent in regions with higher electricity prices. Here, the PV energy is primarily directed to power the load, then prioritised for selling to the grid to generate revenue, with any surplus energy stored in the battery. The backup mode is employed in areas with frequent power outages. Its operational logic aligns closely with self-use, with the difference aimed at raising the minimum state of charge, minimum SOC, to 30%. This then ensures the battery retains a relatively ample charge to cope with extended power outages. The peak shaving mode is used in areas with peak and off-peak electricity pricing policies. During peak hours, energy is discharged, while during off-peak hours, the system is charged. The manual mode allows users to manually adjust the battery's charging and discharging states based on real-time needs. The time of use, TOU, is designed to accommodate more complex scenarios, enabling users to set various operational modes such as self-use, prioritised selling, peak shaving across a 24-hour period. And lastly, in the event of an off-grid scenario, the system switches to the independent EPS mode. Here, the PV energy is primarily allocated to power the loads before charging the battery. In scenarios where the selling price of electricity to the grid is low and the purchasing price is high, the self-use mode is applied. This mode prioritises supplying power from the PV system to the electrical load, followed by storing excess energy in the battery, and finally, selling surplus electricity back to the grid. In the red box in the diagram, the following is observed. The working logic of the self-use mode is as follows. Charging period. When the battery capacitor is less than SOC night, the PV power is prioritised for charging the battery until it reaches SOC night plus 5, at which point the charging stops. If the PV power exceeds the maximum allowable charging power for the battery, excess PV power is redirected to the AC port for electricity generation, which is limited by the AC port power setting. If the PV power is less than the minimum allowable charging power, additional power is sourced from the AC, with the AC charging power not exceeding the maximum charging power setting. When the battery capacity exceeds SOC night, PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus PV power is used for battery charging. Then any excess is exported to the grid for sale. Limited to the grid-tied power setting, if the PV power is less than the local load power, the load is powered by PV, and the battery is not allowed to discharge. If there is no PV, the entire system enters standby mode. Discharging period. PV power is given priority for supplying the loads. If the PV power exceeds the local load power, any surplus PV power is first utilised for battery charging. Then any excess is exported to the grid for sale, which is limited to the grid-tied power setting of the inverter. If the PV power is less than the local load power, both PV and the battery supply power to the load until the battery discharges to under the SOC minimum. If there is no PV at this point, the entire system enters low power standby mode. Other periods. PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus PV power is utilised for battery charging. Then any excess is exported to the grid for sale. Again, limited to the grid-tied power setting of the inverter. If the PV power is less than the local load power, the load is powered by PV and the battery is not allowed to discharge. If there is no PV, the system enters standby mode. The feed-in mode is applicable in scenarios where the selling price of electricity to the grid is high. In situations with ample PV power supply, it ensures the primary supply to the load and directs all surplus electricity to be sold to the grid to maximise profitability. Here you see the operational logic of the feed-in mode. Charging period. The priority is given to charging the battery to charging SOC plus 5%. If the PV power exceeds the maximum allowable charging power for the battery, excess PV power is directed to the AC port for generating electricity, limited to the AC port power setting of the inverter. If the PV power is less than the maximum allowable charging power for the battery, additional power is sourced from the AC, with the AC charging power not exceeding the maximum charging power setting. When the battery capacity exceeds SOC night, PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus PV power is directed to the AC port for electricity generation. If the PV power is less than the local load, the load is powered by PV and the battery is not allowed to discharge. If there is no PV, the entire system enters standby mode. For the discharging period, PV power is prioritised for generating electricity at the AC port. If the PV power exceeds the local load power, surplus PV power is primarily exported to the grid for sale, which can be limited to the power setting in the inverter. If the PV power is less than the local load power, both PV and the battery power supply the load until the battery discharges to under the SOC minimum. If there is no PV at this point, the system enters a low power standby mode. For other periods, PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus PV power is exported to the grid for sale. Any additional excess PV is used for battery charging. If the PV power is less than the local load power, the load is powered by the PV and the battery is not allowed to discharge. If there is no PV, the system enters standby mode. Next, we see backup mode. Backup mode is used in areas prone to frequent power outages in the presence of PV. It ensures that the battery maintains sufficient backup power to cover periods when there is no power from the grid. Here we show you the operational logic to the backup mode. For the charging period, when the battery capacitor is less than charge battery to selected value, the PV power is prioritised for charging the battery until it reaches over the charge battery to plus 5%, at which point the charging stops. If the PV power exceeds the maximum allowable charging power to the battery, excess PV is directed to the AC port for generating electricity. If the PV power is less than the maximum allowable charging power for the battery, additional power is sourced from the AC side, with the AC charging power not exceeding the maximum charging power setting. When the battery capacitor exceeds SOC, PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus power is used for charging the battery first, and then any excess is exported to the grid for sale. If the PV power is less than the local load power, the load is powered by PV, and the battery is not allowed to discharge. If there is no PV, the system will enter standby mode. Discharging period, PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus PV power is primarily used for battery charging. Then any excess is exported to the grid for sale. If the PV power is less than the local load power, both the PV and the battery supply power to the load until the battery discharges to under the minimum SOC. If there is no PV at this point and the capacity is less than the minimum SOC, the system charges the battery at 400 watts AC power until the battery capacity reaches over charge battery to plus 5% without entering cold standby logic. So for other periods, the PV power is prioritised for supplying the load. If the PV power exceeds the local load power, surplus PV power is primarily used for charging battery. Then any excess is exported back to the grid for sale. If the PV power is less than the local load power, the load power is powered by the PV and the battery is not allowed to discharge. If there is no PV, the system enters standby mode. For the peak shaving mode is applicable in time of use scenarios. The system is controlled to charge during non-peak hours and discharge during peak hours. The day is divided into 4 periods, configured on the OLED screen, with settings for B and D time periods and setting time points such as B1, B2, D1 and D2. Charging period A. With enabled, when the battery energy is below maximum SOC, solar and grid power within charge power limits are prioritised for charging the battery. Excess solar power serves the load demand and any surplus is allocated for selling, controlled by an additional parameter. Conversely, when the battery energy surpasses the maximum SOC, solar power takes precedence in meeting the load demand. Any surplus solar power is then directed towards recharging the battery with additional surplus allocated for selling, controlled by export charge. Charging period A disabled. Without using the grid as a source for charging, solar power is prioritised to meet the load demand. Any excess solar power is directed towards charging the battery, with any additional surplus allocated for selling. Charging period BD, enabled. When the load power is lower than the set peak limits, solar power takes priority for charging the battery. Any surplus solar power is then directed to meet the load demand, with any additional surplus earmarked for selling, controlled by your additional parameters. However, when the load exceeds the set peak limits, the system initially purchases electricity from the grid to match the peak limit for the load. Any excess load beyond this, when solar power is sufficient, it is supplied by solar energy. In cases where surplus solar energy is available, it is directed towards charging the battery. If solar power is insufficient, the battery discharges to support the load. Inverter power output equals load power exceeding the limit. Charging period BD, disabled. When the battery state of charge SOC is lower than the reserved SOC threshold, the battery does not discharge. Solar power is prioritised to charge the battery up to the upper SOC limit, adjustable and set within your reserved SOC. Conversely, when the battery SOC exceeds the reversed SOC, solar power takes precedent in meeting the load demand. Any excess solar power is directed towards charging the battery, with additional surplus allocated for selling.
In addition, if you want to choose manual mode, you can manually control battery charging and discharging. In manual mode, the battery can only be charged by grid. Thank you for joining today's webinar. If you have any questions, please ask in the question box. We will help you answer your questions in text in the next 10 minutes. If you have other training needs consultation, you can send an email to training.c.global@solaxpower.com. Thank you for your time.